Beautiful. Okay, so you guys found it. You found it. So this new worksheet for organometallics and alcohols is, well, first of all, it's not an accessible document. You know, accessible documents have to have headers and subheaders that meet what they're supposed to do, and this is an image that is bumping these subheaders off to the side just so that it's organized well, but it's not like, this is something you should be able to look at and interpret easily enough, but it's not something you'd be able to use a screen reader to interpret easily enough, and that's my next goal with all of these. So on this new document, which is more filled out, closer to what all of the other documents I've given you were like, we said that organometallics, which should really just be thought of as negatively charged carbons, they can serve a nucleophilic role in a few different ways. They can serve a nucleophilic role on an EAS reaction, where they can, an NAS reaction, where they can substitute an aryl halide, but they do this by first breaking the aromaticity, getting this resonance stabilized aromatic ring, and then, it's not a resonance stabilized aromatic ring, but this resonance stabilized intermediate, and then kicking off a leaving group. We said that they can also do substitution on alkyl halides, and predominantly primary alkyl halides, because as very good bases, if this is secondary, there's a very high risk of running substitution instead. I want to point out that these two reactions have in common the formation of a carbon-carbon bond by NAS and by SN2. But if we try to run some sort of vinylic substitution, where our halogen is already bonded to an alkene carbon, distinct from an aromatic carbon.
On the SN2 one, you do have like a methyl group coming off.
That's a primary alkyl halide.
Oh, right.
Yeah?
Oh, I wasn't sure if you were going over the document. That's fine.
Oh, no, not necessarily. It's still a primary. Oh, I see, yeah. Actually, this is what I find is the limitation. You know, students all the time ask me, how do I do well in this class? How do I memorize all the information that I need to know? Don't memorize it, first of all. So on this worksheet, I'm using like an isobutyl alkyl halide, which is not to say that isobutyl alkyl halides are the only reagent that react with organometallics, but a useful one because it's an example of a primary alkyl halide. One thing that I like about the isobutyl example is that it shows you there's no rearrangement that's going to occur. It shows you that SN2 is favored, perhaps more so than E2. Thank you for pointing that out, though. If you tried to do this with a vinylic halide, the transition state is what forbids this. So we'd start to see a leaving group leaving and a new group coming in. By the way, we use this little double dagger in the parentheses just to say it's not actually a substrate you can isolate. It's a moment in time. This transition state is too high energy, and so it doesn't proceed. All of that is true if your organometallic is an organolithium or an organomagnesium halide. Because those really do truly behave like negatively charged carbons. But if your organometallic is a lithium diorganocuprate, or in other words, just a cuprate, the copper there interacts with the carbon very differently. It's not so much just a negatively charged carbon. It's not so much an ionic carbon. The lithium we draw as if it's covalently bonded to carbon. Chemists think of it as ionically bonded to carbon, despite portraying it as covalently bonded. But copper, we do think of as more like covalently bonded to copper. A weak covalent bond, an easily transported covalent bond, but not an ionic interaction like we're used to other ionic interactions. So when we look at an NAS reaction, the mechanism is actually quite different. So I'm going to put this in quotation marks. And I'm not going to give you guys a mechanism for this, but I am going to demonstrate that what copper actually does is pulls apart the reagent that it's reacting with. It takes that aryl halide and it bonds the halide to the copper and it binds the aromatic ring to the copper. It's not sending off the carbon as an attack dog, if you will. It's the copper is actually getting in there and doing chemistry first. So you can kind of see how this bond is being dissociated across the copper. Then in that last step, the copper will push off the aromatic ring with a new R group. In fact, the same thing happens in each of these instances, which is why we can say it looks like SN2, but it's not actually SN2. It's more like copper taking everything apart and then putting together new pieces again. I'm not sure that we talked about this either, but the cuprate is not using both equivalences to make these transformations happen. The diorganocuprate brings in two equivalences of an organic group and then leaves with one equivalence of the organic group. In terms of atom economy, it's quite wasteful. You need two equivalences, but you only use one. But in terms of what it can do, it truly is able to run this vinylic substitution because it doesn't need to go through some sort of strange high energy SN2 intermediate. What it can do instead is just pull apart the alkene and the halide without changing anything about their stereochemistry or their regiochemistry, and then it can kick off a new combination. I've seen a lot of organic classes that actually go a lot more in depth into explaining what's happening with copper here. They will use terminology like oxidative addition and reductive elimination. And we look deeper into the oxidation states of the copper intermediates, the palladium intermediates, all sorts of inorganic components of running organic reactions. It usually shows up here in this unit. I tend not to dive very deep into the inorganic components because there are inorganic classes to cover all of that. But I do want to hit on it today. There's two steps happening in each of these reactions. And remember, I'm saying this looks like NAS because it looks like we have a nucleophile, but it's not running an NAS mechanism. So I'm putting it in parentheses. And I'm saying this looks like SN2 because it looks like an SN2 with a nucleophile, but it's not actually SN2. So these two terms, oxidative addition and reductive elimination. Do you guys know what you get when you combine addition followed by elimination? I think we've talked about this actually. I don't know, just to give a math example. Doesn't it look like I've just substituted the two sides of the equation? I've added one thing, I've removed another, I've just substituted them. I've added one thing, I've removed another, substitution. By going through a process of addition followed by elimination, we get substitution. This is actually what we called NAS and EAS. The aromatic substitutions go through addition and then elimination, substitution. Why don't you guys take 3 minutes and decide with yourselves, do you think that step 1 is reductive elimination and step 2 is oxidative addition, or do you think step 1 is oxidative addition and step 2 is reductive elimination? It's okay, you can talk amongst yourselves. Worksheet, Evan. This is the one from last week, but revised.
Thank you.
You're welcome. Hey.
Is there a reason they're using AR instead of, like abbreviation AR instead of PH?
No, I don't know why I did that, to be honest.
That's okay. I just wanted to make sure that.
I think just because this could be any aryl group, it doesn't just have to be benzene.
Okay.
But it did make more sense to put phenyl since it was just a phenyl in my example.
No, I just wanted to make sure I was like,
You know what AR is short for?
aromatic.
Right, which means it could be a lot more diversified if it was AR.
Okay. Yeah, I just wanted to make sure.
Good question. Great question.
for being oxidized?
Yeah, isn't that terrible a little bit? Because oxidation can't happen without reduction. So when we describe something as being oxidative or reductive, we are picking a side. And a lot of times we're not explicitly saying which side we're on, other than describing it as oxidative or reductive. If you're not sure whether it's describing the copper or not, you'd have to try and figure out what else is changing and whether that is going through oxidation or reduction. In organic chemistry, what is our focus always on? The carbon and the change the carbon is going through. So when we say oxidative cleavage, and we use an oxidizing agent like ozone and hydrogen peroxide, we're actually reducing ozone and reducing hydrogen peroxide because we always take the side of carbon. But in these cases, we can use electronegativity to see what change carbon is going through and decide whether the names are going by that or not. Which step looks like addition? The first step or the second step? Well, what is addition? Can we put words to it? I know I taught you how to define addition. In OChem 1, how do you identify an addition reaction? It adds not just something. It usually adds two things. Across a pi bond, often, right, we've got alkene addition reactions. We add two things across the pi bond. Alkyne addition reactions, we can add two sets of two things. Well, I don't have a pi bond necessarily. I'm definitely not adding across a pi bond. But I am adding two things to what? To copper. Copper is going from a di-coordinate to a tetracoordinate central atom. It has two things being added to the copper. So the question is copper being oxidized during that addition? Is it really an oxidative addition? What's more electronegative, copper or carbon? Raise your hand for copper, more electronegative. Raise your hands for carbon, more electronegative. Okay, almost unanimous. So if this is more electronegative, if this is more electronegative, where's the partial negative between a copper-carbon bond? Is the partial negative on carbon or on copper? Partial negatives on carbon. More electronegative pulls electrons to itself. What's more electronegative, copper or a halogen? Halogens, because we say our halogens will have a dipole with our carbons always, create a polar bond. So copper is having a new halogen and a new carbon group added across it, both of which are more electronegative, both of which will pull electrons away from the copper. Is that oxidizing the copper or is that reducing? Go through that mnemonic in your head. I always go through oil rig. Do you guys use other mnemonics besides oil rig? Leo the tiger says grr or something. Okay, oil rig. Oxidation is loss. I saw an Instagram reel, this guy that goes around and says, what's your major? Can I ask you 5 questions about your major? And if you get them right, you win $1. And this kid's like, I'm a chemistry major, I'm a senior. Cool. And then he gets, what describes the loss of electrons? And he said reduction. And he was like confident. And the guy goes, good. Oh, wait, actually you're wrong. Oxidation is the loss of electrons. He goes, oil rig. No, I'm pretty sure that's wrong. I'm like, you said it out loud, dude. Oxidation is loss. Copper is losing electrons to these new groups. Copper is being oxidized by this addition step, oxidative addition. And copper gets some of that electron density back, or rather, it loses the loss of its electron density during the elimination step when it kicks off 2 groups. So it gets reduced again as it gets eliminated. Copper does not behave like lithium and magnesium. Copper can do things that lithium and magnesium cannot do. So because of that, we have this limitation on vinylic substitution happening only for copper and not for our organolithiums and organomagnesium halides. And then we have our acyl additions. And we said on acyl addition that the organometallic, and this one I will try to keep drawn more closely to what you have. We said that on acyl addition, the organometallic, once again, attacks from the nucleophilic carbon and attacks the electrophilic carbon. And then there's an aqueous workup that's needed because organometallics are bases, so they are run in basic conditions. Alcohols are slightly acidic, so we would need to work up this reaction. But this doesn't work with our cuprates. Well, and to be honest, yeah, we're going to say that it has no reaction, but it doesn't mean that it has no interaction. Copper can do some fun things, and copper can pi bond across a pi system. So maybe the copper does interact with the carbonyl, but it just interacts with the carbonyl via some sort of pi interaction. I think you can see that's not really either oxidative addition or reductive elimination because the copper doesn't get two new groups added to it. And it certainly hasn't disassembled the carbonyl in the same way that it disassembles the aryl halide, the alkyl halide, the vinylic halide. So the organolithiums, organomagnesium halides, the Grignards, they do great at acyl addition. They are those negatively charged carbons that are pulled right into that partial positively carbonyl carbon. Cuprates, not so much. And I have no evidence, I have no evidence to support that. And I also have no eraser to erase it. So I really haven't had an eraser. I haven't had to use it yet. Bummer. You guys sitting on it anywhere? So I don't actually have the evidence to support this. That is just a hypothesis, perhaps. An educated guess. Okay, any questions on this? You guys in the back, you got pictures or you got it copied down on the left-hand side? Okay. The other thing I wanted to point out when I gave you guys the preparation of a diol, I believe I told you OSO4 is all that you need to put down, and that is still true. I will accept your answer if all it has is OSO4, but I think I also told you guys I'm always shifting towards better and better use of reagents. Especially closer to what you guys will see on your active assignments and out in the real world. And rather than just having osmium tetroxide, which remember is OSO4 and not O5O4, We also need a peroxide, a tert-butyl hydroxide peroxide. And we need a solvent tert-butanol, or this can be run in cold KMnO4. But I just wanted to remind you guys that I will be representing osmium tetroxide with its corresponding peroxide and alcohol. I want you guys to be aware of that so that when you see OSO4 with other stuff, you don't have to question, does that mean just OSO4 or is that different than OSO4? Because you guys know how different combinations of things change everything. X2 alone is different than X2 with water, is different than X2 with alcohol. So I just want you guys to know OSO4, I'm just adding on the necessary other reagents there. You are welcome to keep it as OSO4. For my future sections, maybe not so much. All right. And then, as Mimi said, the other reaction I didn't give to you guys is, I still didn't put page numbers on these things. It's on the reactions with alcohols. And it's a vicinal diol oxidation. To my knowledge, this isn't named after a dead man. So you can either just recognize it by what it is, or you can recognize it by its reagents. I always think this name is going to help better. The molecule that I've given you is very small, but it highlights the two cases. Your diol could be on a secondary carbon. Your diol could be on a tertiary carbon. Those are the most common cases that I've seen this reaction used in. I don't know that there's a limitation to this being used on a primary alcohol. Would you guys describe this oxidation using the context of other oxidizers we've already talked about? Would you describe this oxidation as a mild oxidation or a strong oxidation? And take a look at the other side, page 3, where you're actually given those examples of strong oxidation and mild oxidation. Would you describe this vicinal diol oxidation as mild or strong? Mimi, you're looking at the next page like you've never seen it before.
I guess I'm just confused about the last two reactions because they seem to come out of the same
I agree.
dynamic.
When that secondary alcohol is oxidized in strong oxidizing conditions and in mild oxidizing conditions, the same thing happens. And that's because of how many hydrogens can be removed. Oxidation can be thought of as a loss of hydrogens to the carbon. It's not always the case, but when that happens, it is oxidation. And that secondary alcohol carbon only has one hydrogen to lose. The primary alcohol carbon has two hydrogens to lose. When one is lost, mild oxidation. When both are lost, strong oxidation. When the methyl alcohol is oxidized in mild conditions, one hydrogen is lost. When it's oxidized in strong conditions, all three hydrogens are lost. So would you describe this as mild or strong? Why?
Because both hydrogens are lost.
I disagree.
Is there like a,
There is only one hydrogen. Would you agree? There's only one hydrogen here. And it's not lost. Instead, the oxidation comes from this bond cleavage, the carbon-carbon bond cleavage. That's where the oxidation happens. The carbon-carbon bond is lost, and then a double bond to oxygen is made. I would say this is mild because it retains an aldehyde. And we know that aldehydes can be oxidized further. We saw last week how methanol can be oxidized to formaldehyde, can be oxidized to formic acid, can be oxidized to carbonic acid. We saw that a strong oxidizer pulls out one hydrogen and then pulls out another and then pulls out another. A strong oxidizer doesn't leave you with an aldehyde at the end. A strong oxidizer oxidizes aldehydes. So I would say this is a type of mild oxidation. And the reagent, do you recognize it? Could you name it from your Gen Chem knowledge? It's one of my favorite acids, mainly just because of its name. Okay, I'll give you two options. Iodic acid or hydroiodic acid. Raise your hand for iodic acid. Raise your hand for hydroiodic acid. Hydroiodic acid is HI. Like hydrochloric acid, hydrobromic acid, hydroiodic acid is HI. Periodic acid is not, or sorry, iodic acid is not correct either because iodic acid has 3 oxygens. Iodous acid has 2. Hypoiodous acid has 1 oxygen. Hypoiodous, iodous, iodic, periodic. It's just like with the chlorates. There is hypochlorous, chlorous, chloric, and perchloric acid. A scale of how many oxygens are actually there. So this acid is, can you read that? Do you want to read it? Kwana? Kwankwa? Brenna?
It looks like periodic, but it's periodic.
Isn't that amazing? Periodic acid is what it looks like. And it's not. It's not even close. But what a good name in chemistry, right? We've got the periodic table, and we've got a periodic acid. Which if you named it that way, you'd think it's only an acid from time to time. Like it's an acid, but only periodically will it behave as an acid. Periodic acid. That's good stuff. So be careful if you ever see it written out. If you ever read what happened when the reagent periodic acid was used, just remember they're actually asking you about periodic acid. And to put some context, that's HiO4. The other end of the spectrum is hypoiodous acid, which is HiO. Oh, right, I have no eraser. All right, now at the bottom of the 3rd page, I've got provide the reagent and product. I'd like you guys to take the next 5 minutes. Where you have a reagent, draw the product. There are 2. These are not the same reaction, going down and going to the left. So you're drawing 2 products. I hope that's clear. Draw a product down, draw a product from the left, add a reagent to the right, add a reagent up. Take the next 5 minutes. Feel free to work with each other, especially to check your work and see how you're doing. Brenna, did I give you a new sheet? It's the same as last week's, but not the same. Revised. You're welcome. And what we were going through this morning were things that I left out last week that show up on this. Oh. This is good. This is good. Actually, I want to see methanol with it. Okay. NABH4 with methanol. This is good. This is not. Not quite there. Okay. Close. Yeah. Very close. Great. Not quite. Not quite the product that we get. This is good.
Yeah. That's cool.
Your prediction has created a carbon.
Oh.
Do you see how there was an oxygen there and not a carbon?
So would this one stay the same and then that one?
Yeah, well, we know that esters react to LAH. So we know that this should get reduced to an alcohol. But remember what all of these had in common? They were primary carbonyls, and they gave primary alcohols. So there's a secondary carbonyl, secondary carbonyl, secondary alcohol, secondary alcohol, primary carbonyl, primary carbonyl, primary alcohol, should be a primary alcohol. You'll also remember from class that we said that each of these, or a few of these, except for the aldehyde, had a second byproduct. So think about what that other product would be. Yep. This has 3 bonds, correct? to each carbon and to the hydrogen. That makes it positively charged. There's nothing wrong with being positively charged, but it's unlikely to be the major product. And remember that esters get reduced to primary alcohols.
Yeah.
And I'm seeing a protonated ether.
Oh, yeah.
So try to think about how to draw it as a primary alcohol and think about how there's another byproduct.
Okay.
We said there's something else that also forms. Yeah. So this would require 1, 2, just like you see here. But then these would give the same product, would you agree?
Yeah, that's right.
And actually, we know that it can't be that reagent because we see that the ester is still intact, and esters are reduced by LAH.
Oh yeah, because it goes from because that's a secondary
Mm-hmm.
compared to the primary.
Yes.
Okay.
So the ketone should, we see the ketone does get reduced, but we see the ester does not. So LAH can't be the reagent going across. Down below, you used PCC, and we said that PCC will take any type of alcohol and oxidize it, or actually rather primary, secondary alcohols and oxidize it. So how come this secondary alcohol isn't oxidized? Actually, it's the same product that we see up above.
Oh my goodness, yes it is.
Yes, it is. So it's probably going to be something different.
I can ask him this.
You talking to me?
Yeah.
Ask me. Okay.
You can't use these with tertiary. You have to use organometallics.
To make a tertiary alcohol.
Oh, but if you have
A tertiary alcohol, nothing will happen to it. If I have a tertiary alcohol and I oxidize it with a strong oxidizer, or I treat it with a strong oxidizer, nothing happens. Because there's no hydrogen on the carbon to be removed, so it can't be oxidized. It won't be oxidized further. Well, except I guess here's a tertiary alcohol. But it's part of a vicinal diol system. And it gets oxidized because of the ability for the vicinal bond to be cleaved. I've never referred to it as a vicinal bond before, but that regiochemistry made sense, right? The bond that makes it a vicinal diol, that can be more easily cleaved because of the diol. Here, nothing happens. Where am I? You guys want more time to solve it? Good struggle? Good. Think you got it? Think you got stuck?
I don't know what happens, like, where does that go? Because I realize now what my mistake was. This is a primary
Yeah.
mono to a primary alcohol. But I'm like, what about this guy? Like, how does
Yeah.
it get kicked off?
So do you remember on our notes last week, we actually said that there's another byproduct formed at each of these?
I think I have it. Yes, I remember.
What is the other byproduct formed when the ester is reduced?
An alcohol.
Oh, okay, so that's where it goes.
So is it still attached to the ring, the alcohol?
Yeah, I mean, what you did here was you just cleaved the OR group and made an alcohol. So all you have to do here is cleave the OR group and you get an alcohol.
Okay.
There it is.
Interesting.
Great work.
That's kind of powerful.
It's fun, right?
Yeah.
I hear a lot about cleaving and stuff.
Mm-hmm.
Without seeing it.
So we've got an ester,
Yeah.
and we know that esters get reduced to a primary alcohol, but we didn't say they get reduced to a primary alcohol still attached to an ether. So there really should just be cleavage of that OR group. Where you've got an ester, cleave off the OR group.
Okay. So a cleave on this side.
There you go.
And then this
But now-
one the other way.
But now, Justice's question is, what happens to that group? Because it's still a part of my chain, so I have to know what happens to it. Yes. It gives a byproduct, or in this case, just a separate part of the molecule.
Gotcha. And then this one doesn't cleave though?
No, it won't
Just
be
not
cleaved.
in OR?
Yep. Because actually, it is the secondary carbonyl.
Ah, I see.
Good. Did you figure it all? Yeah. So we know that esters get reduced to alcohols. So we know that it won't show up as an aldehyde. There is actually a way to do that. We'll talk about it after the midterm. So we know that the carbonyl carbon becomes an alcohol carbon. The carbonyl becomes an alcohol. But last week we said that each of these produces another byproduct as well. Some other thing that is kicked off, like the carboxylic acid also makes a water byproduct. The acid halide also makes a hydrogen chloride byproduct. The ester, do you remember what byproduct the ester formed? Do you have it in your notes somewhere? I'm going to send you to find it first. How do you guys feel?
Just iffy on these. Just because it's only one.
So you're saying PCC does, it oxidizes one alcohol but not the other here, but then PCC oxidizes the other alcohol but not the one here.
It was
Okay. Can you describe, is there any difference between these two alcohols?
this one could do resonance with this aromatic ring.
Yes. We say it's a benzylic alcohol. It's on a benzylic carbon. And benzylic is the one just off of the ring, the one that's conjugated. So do we have a reaction that is selective to benzylic alcohols and does nothing to other types of alcohols?
The MnO2.
I agree. Here's a benzylic alcohol that gets oxidized. Here's a non-benzylic. Well, it's not even just benzylic, is it? It can also be allylic that gets oxidized. Now, PCC didn't have any sort of constraint. So,
Also could be both.
good thinking.
Makes sense.
On the other one, your ester, you've got an ester and a ketone that are being reduced. What we can say is that the ester is a stronger group, less reactive, because the ester is sometimes reduced and sometimes not reduced. But the ketone is always reduced. So, why do you think that in this reaction, the ester will be reduced, which is the right product that you drew, but the ketone would stay unreacted? Ketones react in that same environment. In fact, ketones react in milder environments. Okay, I'm going to leave you with that. Esmeralda, you might have to convince Pamela on what that's going to mean. How you feeling? Okay. How about you guys? This is good. This one would oxidize both of them. Yeah. So we need something that's actually going to be selective in oxidizing one but not oxidizing the other. And can you describe the regiochemistry difference between those two alcohols? Could you define them differently? I would say they're both secondary, but one is benzylic. What does that mean again? Benzylic is the position just off of the benzene ring, and a benzylic alcohol gets oxidized selectively, where non-benzylic alcohols don't get oxidized.
I see.
Good. All right, did you guys find what I was talking about here? You've reduced your secondary alcohol or secondary ketone to an alcohol, and then this became an alcohol. And what about the other carbon? The other carbon goes from a CH2 to a CH3. When we went through our reductions, we said that the carboxylic acid gives off a byproduct of water. The acid halide gives off a byproduct of HCl. The anhydride gives off 2 equivalences of alcohol. We said the ester gives a secondary alcohol from the carbonyl, and then it kicks off a second alcohol. Whatever that OR group is becomes another alcohol. Last week we did an example where we said, how could we use reduction to produce methanol? And we said that if the ester had a methyl group, then methanol gets kicked off as an alcohol. So whatever that ester linkage is, whatever that OR group is, becomes an alcohol. You bet. When we reduce that ester, we get a second equivalence of alcohol. Whatever that OR group is, becomes an alcohol. And would you agree that this reduction doesn't actually even really make an alcohol? Because it doesn't look quite like that. It looks like that, but mixed with an ether. So when we have an ester, we just cleave that OR group. That bond between carbonyl, carbon, and oxygen goes away.
So this.
Yep. And then both sides become alcohols.
Okay.
There you go. Did you find it? Looks good. Yeah, you got it. Oh, don't forget, that's a 1,2. First LAH, then H3O+. And the 1,2 is actually pretty important there. Our ester should get reduced to give a byproduct of alcohol. Carboxylic acid gives a byproduct of water. Acid halide, a byproduct of HCl. Anhydride, a byproduct of a second alcohol. This one just gives ROH, whatever that group is. So we cleave the OR group.
They would just add one? Okay.
But I think you lost a carbon in there. I think by doing that, you lost a carbon.
Oh,
Sorry.
I see, sorry.
No, you're good. This is good. This is good. This is missing an alcohol.
So would it also get added here as well when it breaks?
Yes, but actually you did the same thing Jordan did. You turned a carbon into an oxygen, and we need to keep that carbon as well.
Oh, so it would just basically like.
Oh, I think you added the alcohol to the,
Wait, I'm confused there.
yeah.
So leave
That carbon
that
becomes an alcohol carbon.
this one.
Mm-hmm. Just like you had it drawn before, actually.
Oh, so just like this.
Yep. And this carbon becomes an alcohol carbon. Now that's, you had that carbon drawn,
But I lost
yes, and then you lost it. All right. You're welcome. So last week, I want to remind you guys, last week I was asking for ways to use a reducing agent to form methanol, because we had looked at how we could produce primary alcohols, we could produce secondary alcohols. We know we can make tertiary alcohols by acyl addition, not by reduction. But I asked, how could we reduce something to get methanol? And we said if it's a mild reducing agent, I have to use something that can react in mild conditions like formaldehyde. But we said if it's a strong oxidizer, like LAH, which remember needs to be written as 2 steps, because LAH cannot exist in the presence of acid, and we need the acid to make the alcohol. If we have something like LAH, and a methyl ester, then we get an equivalence of methanol as a byproduct because the ester linkage, the OR group, becomes an alcohol. Plus, whatever else is connected there also becomes an alcohol. We get this CH2OH from the carbonyl carbon. So when we're looking here and we say we've got a ketone and what's called a lactone, because it's a cyclic ester, the ketone and the lactone get reduced. Ketone gets reduced to a secondary alcohol. That's easy. Here's the mistake that I saw most of you guys make, which was to draw this as the reduced product of the ester. Now, this is actually a functional group that we're going to talk about in a few weeks after the midterm. I think that we can call this carbon a geminal etherol. On the same carbon, geminal, remember geminal means twin? On the same carbon, two functional groups, twin functional groups, an ether and an alcohol, a geminal etherol. We're going to talk about it in a few weeks as an acetal. That's the name that's given to it. Actually, it's a pretty predominant group in sugars, a carbon that is bonded to both an ether and bonded to an alcohol. I'm sorry, actually it's a hemiacetal because it's halfway to an acetal. Both hemiacetals and acetals are big parts of sugars. But this is not the functional group that we predicted esters would form. We said an ester as a primary carbonyl should form a primary alcohol. The primary carbon of the carbonyl carbon becomes a primary alcohol. So I was looking for this cleavage. When I encouraged you to find that cleavage, then a lot of you got to this and said, well, I don't know where to go from here. Either that oxygen, something needs to happen to it, or the oxygen needs to just go away. And I'll be left with just those two carbons. This is what I saw a lot of you end on eventually. The ester would get cleaved into a primary alcohol and then just a normal carbon chain. But that's not what we predicted last week. Last week, we said the OR group gets cleaved to form a second alcohol. In this case, that alcohol is attached to the molecule still, and there is nothing wrong with that. Very, very legal. Up above, we see the ketone reduced. We do not see the ester reduced. We know that the ketone is reduced in both mild and strong reducing conditions. So we just need our mild reducing agent, sodium borohydride. With methanol, you do not need to list this as 1,2. In fact, you shouldn't list it as 1,2 because it all gets dumped in together. But there is another way that you can represent it if you want to, a way that you'll see in some of my materials, which is first NaBH4, then H3O+, much like what you see with LAH. And can someone remind me why does sodium borohydride reduce the ketone but not the ester, and LAH reduces both the ketone and the ester? Why is this a stronger reducing agent? He's trying to zoom in on his paper. Yeah. Boron. Right, aluminum is less electronegative than boron. So the electronegativity difference between hydrogen and aluminum is even greater than between hydrogen and boron. And that difference in electronegativity is what makes the hydride as strong as it is. Perfect. Okay, on our other side, we've got two types of alcohols. It's important that you can identify the characteristics of those alcohols. One is a benzylic alcohol because benzylic is placed next to the benzene ring. Benzylic alcohols and allylic alcohols are stabilized by resonance. So we can use a radical oxidizer like MnO2 to oxidize selectively the benzylic or allylic positions. If I use something like PCC, it doesn't discriminate against radical stability or not. It doesn't discriminate against primary or secondary. PCC will take one hydrogen away from both of these positions and turn both ketones, the benzylic and the non-benzylic, into, nope, sorry, it'll take both secondary alcohols and form ketones. How could I take the bottom right reagent, how could I take this and form a structure with two aldehydes? Or maybe I should just say, how could I react it and form two aldehydes? Using, actually using chemistry that's on the board already and in your sheet, in your notes. Periodic acid. I have a vicinal diol, and that vicinal diol is two secondary alcohols. So when I introduce this to periodic acid, it cleaves that bond between the two alcohols. And since they're secondary alcohols, since they already have a hydrogen attached to them, that cleavage of the carbon-carbon bond maintains the hydrogens and creates these two aldehydes. Now, to be fair, this bond line structure was easy enough to draw because I just preserved the bond line structure of the starting material. But this is not really a normal zigzag. So if I were to redraw it, two CH2s before my aldehyde, two CH2s and then my aldehyde, this is maybe how you might see the structure just in a normal zigzag pattern, normal bond line. But the structure in orange is easier to predict because it preserves some of that chemistry. Jordan, I think you added a carbon to your second aldehyde. CH2, CH2, carbonyl carbon. Oh no, it's just a long bond. I'm sorry. Sorry to call you out like that. CH2, 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 CH2. Okay. I want to use the rest of the time, instead of diving into ethers and epoxides right now, although we probably would be done by the end of the class, I think I want you guys to spend more time just on this selection of reagents. I want you guys to work on the synthesis problems. Is that the last page, the very back page is all synthesis. You have 20 minutes. The time is yours. Please ask me as many questions as you can as you solve your syntheses. Do you guys remember my, my tips on synthesis? Map your carbons. Figure out, are you adding any carbons? Are you losing any carbons? What carbons are going through the change that is present in the synthesis? Brainstorm. Does it look like you need to do acyl addition because you form a tertiary alcohol? Does it look like you need to do vicinal diol oxidation? Does it look like you need to do reduction or oxidation or substitution or elimination? And 3, work forward and backwards. Don't just start with the starting material and think you can figure your way out to the product. Look at the product and figure out what it could have come from and then meet in the middle as often as you can. That's usually the best way to do it. Okay, the rest of the time is yours. Oh, and by the way, the homework I re-uploaded. So if you are someone that has already downloaded this unit's homework, I will still grade it as it is, but I would recommend that you look at it, at what has been changed. Because the homework doesn't have mechanisms. This unit is a synthesis unit for our class. So it's 2 synthesis problems you need to solve. Just be aware of that. That's why we're going to be doing a lot of synthesis practice in class. And guess what you can expect to see on the unit test? Synthesis. I know. Oh, that was kind of funny to see. I'm sorry. Sorry to call you out like that. Dude, throwing you guys under the bus all day here. I'd never seen it, but I knew exactly what you were doing too.
I didn't even notice until you said it.
What the heck do you do with this one? Because it loses a carbon.
Oh no, does it?
Yeah.
Okay. Typo on the top right. Synthesis. Thanks.
Yeah,
Thank you.
it was tough. I don't even know how I got here. I think I don't know. I think I used like 50, like almost all of the retries until I finally got it. Because I was like, what am I missing?
I don't even get it.
There should be 6 carbons. That was not an intended. That's a mistake.
Not this.
This is not it. What's it?
This, sorry.
Oh, yeah, that's
This
fine.
was the homework,
Mm-hmm.
but I just don't know get this one.
Oh, well, for one, I don't know what attempt you're on and like what you've changed, but you're not showing alpha cleavage.
Well, at this point, I was like, I don't, because this would be cleaving here, right? Doesn't it just have to have 4 different? Yeah. So it have to cleave on this side or that side, right?
Yeah, well, actually, the positive.
wait.
So remember, the fragments in mass spec have a positive charge.
Okay.
So if I have something like a CH group and it's bonded to a carbon chain over here, but let's say it's also bonded to an alcohol, and this is the positively charged fragment, well, the alcohol can donate in electron density, and it can help stabilize that positive charge, which makes it a more stable fragment, which makes it more likely to form. So we look for, here's like an R group. We look for alpha cleavage, where alpha is our functional group carbon, because that functional group usually has some way of stabilizing it. So find the alpha carbon, and then cleave the carbon groups next to it, one at a time. Okay, what other mistakes did I make? Here's a challenging thing about this. How do you decide to count aqueous workups? Are aqueous workups their own step, or are aqueous workups included in the step? I tend to consider them as included in the step. Aqueous workups are not their own step. Same thing with like hydroboration oxidation. Technically, it's a 2-step process, but you're never going to use one without the other.
I think I figured it out. this, right? The per iotic. Took
Yep.
it and then did the reduction.
Yep.
Okay.
Great. That's exactly it.
Question about so I've been doing a lot of like the old midterms, and I
Yeah.
noticed that like there were questions about like, are you still planning on doing like NMR and that stuff as bonus points, or like on the actual test?
Interpretation of spectra, bonus points.
Okay.
Multiple choice questions about predictions in spectra, graded points.
Okay.
You guys remember that one of your earliest analysis assignments was find the functional groups and predict the IR signals? That is because I wanted you guys to be refreshed with, I'm actually thinking of expanding that one to say submit the functional groups, submit the IR, and submit the number of NMR signals you might expect, right? Because there's actually a lot of NMR on the exam. You'll probably notice it'll say like, consider the molecule above, which of the IR signals is not predicted? Or which of the following H NMR signals is expected in the structure above? So you still need to have an awareness of spectroscopy, but you will not have to analyze a spectrum. My understanding about standardized testing, like the MCAT, is that they never show you a spectrum, but they expect you to understand where things are predicted to be. Where does a CO double bond show up? Where does the signal for an sp3ch show up? So you will see that in there. You'll see spectra, but you'll see spectra as bonus points.
So will there be chemical shift questions on NMR, or is it more just like chemical environment questions?
Chemical shift, sometimes splitting pattern and integration, sometimes all of them together. I want to say even just in the last exam, I gave like which of the signals is not predicted in the aromatic structure up above, and it said a 1H doublet at 1.8 parts per million, a 2H doublet at 1.8 parts per million, 3H between 4 and 6, 3H between 6 and 8.
Gotcha.
And I also give you that correlation table
Okay, that's what I was.
on the midterm.
We're gonna have the table, or is it just?
This is where my colleagues push back on me and say you're hurting your students by giving them those tools because they'll never learn it. In my opinion, you were just going to memorize it anyways. So I'd rather that you not memorize it and instead learn how to use a useful tool. Because when you are studying for that very high stakes mid-MCAT exam, you cannot just go in there with memory. You've got to have tools and resources that you know how to use. And I think this is a good tool and a good resource. So, plus, in the field, in grad school, I would have never tried interpreting an NMR without some sort of resource next to me. I'm not just going to wing it and blindly guess and then later go back and try to prove that my memorization was right. Instead, I'm going to prove it right then and there by using a resource that I have right with me. It's like in your lab notebooks. We require you guys to write down melting points, boiling points, hazards, because I don't want you going in there and memorizing it. Instead, I want you to have a resource that you can rely on, a tool that you know how to use in the event that you need it. Brain dead is acceptable. Time of brain death, 9:25 and 47 seconds.
I'm trying to think of what I'm gonna do this weekend, so I'm like too focused. Too many things to do.
It's only Tuesday, you're already...
Well, I have to have my schedule, like, because I work and I do research to like do like test our classes and stuff. So I kind of have to like, my next 2 months are so mapped out. But then sometimes I'll get like, family events with work. Or hey, we have a baby shower or a birthday party or whatever. And I'm like, I have to see if I can
Great work. Awesome. Actually, I think you've misunderstood how periodic acid works. Periodic acid won't do anything to a vicinal diketone. It'll only do, periodic acid will only work with vicinal diol. Diol oxidation. Well, there's a diol, but that's not a diol. You get the difference? Diol is telling us 2 of what? 2 alcohols. Is that 2 alcohols? I agree. So periodic acid wouldn't be expected to do anything with it. So if you wanted to use periodic acid, maybe you should use it first. But you know what it forms, right? It forms aldehydes and ketones, which is not what we want in the product. Tell me.
So for the, well, it's not related to this, but for the extra credit,
Oh, we don't want sodium iodate. We want periodic acid, or sodium periodate. So instead of Na, I wonder, did you find that online? Did it have anything else written with it, like H2SO4?
I don't remember.
Okay, that's very similar, right? Like it's doing the same thing. It's actually just a salt version of this acid, which we use a lot. We will say use sodium dichromate when really we're saying chromic acid, because a salt is an easy way to get that thing present and then provide a stronger acid, and now it is the acid. So if you are going to use NaIO4, I'd want to see something else like H plus with it. Or just use H instead, HiO4. Biotic. What did you? Sorry, you had another. Did I answer your question? I don't think I did.
No. Do you have a cap for like? So I know it's like 30 extra points that we can earn.
Towards homework.
Right.
Mm-hmm.
So like, let's say we get 100% on homework. Can that still be? Oh.
You can go over 100% on the homework,
Okay.
but remember, homework is
5.
25% of the grade, and 30 points is something like 1.5 active assignments. So it's, yeah, I am okay with it. I don't cap it at 100,
Okay.
but it's not. I guess that those 30 points could be a tipping point in a grade. Like if you were at an 89, and then you did all those extra credit assignments, you could probably get up to a 90 or 91. But I don't think that all of that extra credit is going to bring you from a C plus to a B plus, right?
Yeah.
Do them, because it's free points. Even if you don't finish them, you can earn partial credit for what you did finish. But remember, they're not mine. So the way you see things presented on there is just not how you'll see them presented by me. That's another limitation of them, or benefit. Depending on how you look at it, because now you've actually seen it in more than one way, and you get a better awareness of it. But no cap.
Okay.
Did you have a follow-up on that?
No, that was it.
Okay,
Thank you.
you're welcome. Did I look at all of yours? Yeah, exactly that. Great work. Oh, did I look at this one? So I think you're adding too many carbons here. For one, this is 1, 2, 3, but then I only see 1, 2. But this would be 1, 2, 3, 4, 5, and here I see 1, 2, 3, 4. And then don't forget, 1, 2. First, second. Just like in lab last week, we added the Grignard, and then we came back and we added the hydrochloric acid. But we didn't add the hydrochloric acid with the Grignard. So think about what your carbon chain should be. Okay, is this a CH2 double bonded to lithium? Because it does look like you're then just adding the CH2. How many bonds to carbon does that make? Too many. Now, this also is not quite the right reagents. HBr and H2O2 runs anti-Markovnikov HX addition. But we are not looking for HX. We're looking for halohydrin addition, which according to our Ochem review reactions is X2 and water, not HX and hydrogen peroxide. So I would say start from the back. You know that you want to do an halohydrin addition, and you know that that means there must be an alkene. Now you know what the structure of the alkene is. Now can you try to get to that alkene through the synthesis? 5 minutes left. What answers can I question?
Me.
That's so rude. I'm sorry.
If you have this,
Yeah.
like, and you oxidize it,
Yeah.
does it take a carbon then?
Nope.
Become carbon dioxide and water? No.
No. No, only methanol becomes carbon dioxide and water.
Oh, okay.
Primary alcohols don't. By the way, I'd love to see, this is great to show it as a 1-2 over the arrow. But remember when you solve a synthesis for a test or an exam, you need to show me the intermediates that are formed.
Okay. Okay, I can do that.
And I'd like to see NABH4 with methanol. Good.
I'm gonna double check that.
Perfect.
Okay.
That's it. How about this one over here? Perfect. Great work. This is great. Yep.
Is this right so far? I'm not sure.
Well, HBr with an alcohol would actually just, reactions with alcohols. HBr with an alcohol swaps out your alcohol for a halogen. But let me ask you why you want to put a halogen at that position. What is your goal? You've got to...
We can kick it out and add the aromatic ring.
Okay. But this carbon, benzene, and maybe you're not done drawing on it, it doesn't really have a lot of reactivity. Like, it's not nucleophilic. It can be electrophilic, but you haven't really shown me the reagents for NAS or EAS. Right? They won't just form a bond just because. You might think about how do we form tertiary alcohols and what starting material could be there before we form tertiary alcohols. And that might give you a better idea of what to do with your secondary to get to that tertiary.
Thank you.
You're welcome. Do you recognize that structure from lab?
Uh-huh.
Okay. Leverage that.
Yeah.
Okay. This is great, but I do want to remind you that when I have you solve syntheses for points on assignments, I want to see all the intermediates. So show me what happens after reduction, and then draw an arrow from that with sulfuric acid. This one doesn't give us exactly that, because a diol gets oxidized to carbonyls. So periodic acid will cleave the carbon-carbon bond, but won't leave you with alcohols. So you will need a second step.
Thank you.
You're welcome. All right, thank you guys for your time. We're gonna, we have more time to go through this tomorrow. I have more synthesis coming tomorrow. You might want to look at the Unit 3 homework and look at solving the first two problems, which is, or the first synthesis, the two options, which is revolving around alcohols. The second question revolves around epoxides, which we'll look at tomorrow. Enjoy the rest of your day. See you tomorrow. Evan.
So, well, first of all, this was my idea on the first one. I kind of split it
Great.
like there and then.
Perfect.
Okay.
That worked exactly right.
I didn't do this one, but I mean, it's like our lab, so it's good. I can at least review if I need to.
Good. Leverage the idea that you know what it might come from in lab.
Yeah, for sure.
Perfect. Yep. And exactly right. Yep.
I need to catch up on some videos for section 2. But just I can't think of where I would come from this.
Yes. Either reducing agent, strong or mild. Yep.
Like it seems like on this one I could do like an oxidation of some sort. You know? But it almost seems like if that were to be true, then I could just go straight from here to here. Like,
Huh. So something that oxidizes the primary alcohol to a carboxylic acid. Would that same reagent do anything to a secondary alcohol? Because you have a secondary alcohol that you're trying to leave alone.
yeah, so if I did do something with the secondary, it would also make a double bond
Yeah.
there. So I could do that and then somehow reduce just this one, which I can do somehow.
Maybe somehow.
Maybe somehow with, wait. Well, this one has no reaction, right? So if I did NaBH4
Has no reaction
with
to the carboxylic acid,
carboxylic acid
but does react
with the whatever second degree alcohol
with the ketone.
ketone.
Good. What you got, Justice?
For the lab reports, can we for the results, can we show the results in various tables?
Yeah. Yeah, you can have multiple tables. That's great, actually, because each table is probably going to have different needs.
When redoing the assignments, I have until tonight, right? To turn in the